Thus far, all of our systems have had one solution. For example, let's say these two lines make up a system, and let's say this point right here is 1, 3. Then this system of two linear equations has one solution, precisely the ordered pair 1, 3. All of the systems we've seen so far have had one solution. But is it possible for there to be a different amount of solutions? Could there be 2? Could there be 3? Could there be none? What's possible? Well, let's think about, is there 2? Is it possible to have 2? If you had this line right here, another line's got to come through and hit it. There's one spot. Is it possible to then have another point where it intersects? Well, it's not possible because we are only talking about straight lines here. You can't have this sort of bend. So it's not possible to have 2 solutions or even 3 solutions or 4 or 5 or 6. So there are a couple of other possibilities still. Can you think of them? Well, one example is if you've got a system made up of parallel lines. By definition of parallel, the 2 lines will never intersect, so this system of equations has no solution. So it is possible for there to be one solution. There's possible for there to be no solutions, i.e. 0 solutions. And by 0 solutions, I do not mean the point 0, 0. By 0 solution, I mean it has no solution. And technically, there's even a third scenario. Let's say you've got this line, and then you've got another line in red, which is actually the exact same line right on top of it. Then that means every single point on the line is a solution to the system. And there are infinitely many points on a line. So it's also possible for there to be infinitely many solutions. These are the 3 possibilities. A system of 2 linear equations can have one solution, no solution, or infinitely many solutions. Those are the only 3 things that can happen. Let's take a look at some specific examples. How many solutions do each of these graphed systems have? Well, the one on the left here, it's got precisely this one solution right there. This system with these 2 parallel lines, they're not going to cross, so that has no solution. And this one, although we can't necessarily tell, let me draw it in, you've got 2 lines laying on top of each other. So there's that red line there, and there's also a blue line right on top of it. In that case, there's infinitely many solutions. But what if we're not presented with the graph of a system? How could you find out if it has one solution, no solution, or infinitely many solutions? Let's take a look at a couple of specific examples to see when we might end up with no solution or infinitely many solutions. Let's solve this linear system here. As of now, we only have 2 techniques for solving a system. One is the graphing method, one is the substitution method. In general, I would not recommend using the graphing method unless you're basically told to, because otherwise we need to get grid paper, we got to graph very carefully. There's a variety of weaknesses when it comes to the graphing method. So we'll use the substitution method, which is a 4-step process. And the first step is isolating one of the variables. But notice, y is already isolated in this top equation. So we're going to jump right to step 2. We're going to take the 4x plus 1, and we're going to plug that in place of y down here. So we've got negative 12x plus 3 times in place of y, in parentheses, we're putting in the 4x plus 1, equals 3. Notice we now have an equation with just x in it. Step 3 is to solve that equation. So if we distribute, we've got negative 12x plus 12x plus 3 equals 3. Of course, on the left, if you combine like terms, you've got 3, and on the right-hand side, you've got 3. What happened to x here? Did we do something wrong? Whenever you end up with, after solving your equation, you feel like you've done it properly, if you end up with a numeric statement where the variable is gone, this should tell you something. You are in one of the 2 special cases. The typical, most normal case is when you get one solution, but the special cases are what I'm calling when you get no solution, or infinitely many solutions. So if you get a numeric statement where the variable has fallen out in step 3 of the substitution method or step 3 of the elimination method, which is something you'll be learning soon, this means that you either have no solution to the system or infinitely many. Well, now we want to do a little bit of an analysis to figure out which case it is, and then we're going to come up with a shortcut rule of thumb to help you decide from here whether there's no solution or infinitely many solutions. So first, the analysis. What I want to do is write both the equations in y equals mx plus b form and then compare them. Well, the top equation, y equals 4x plus 1, is already in y equals mx plus b form. So let's put this one in y equals mx plus b form. First thing we need to do is add 12x to both sides to get rid of that negative 12x. That would give us 3y equals 12x plus 3. And then we need to divide both sides by 3. Don't forget that this 3 over here would divide into the 12x and into the 3. This would give us y equals 4x plus 1. So notice this equation is exactly the same as the top equation. So that means the lines are exactly the same. Does that imply there's no solution or there's infinitely many solutions? No matter what the line looks like, if the two lines are exactly the same, that means they share infinitely many points. That means there's infinitely many solutions to the system. So we've got infinitely many solutions to this system. I'm going to give you a rule of thumb shortly to show you why there's infinitely many solutions based on just looking at this numeric statement right here. Let's solve this system and see what happens. Let's go ahead and use the substitution method. And for step 1, the variable that I'm going to isolate is this y right here. Seems to be the easiest one to do. So to isolate this y, you'd need to subtract 2x from both sides, which would give us y equals 1 minus 2x. Now step 2, we're going to take this 1 minus 2x and put it in place of y down in this equation. You've got 3 times the quantity, 1 minus 2x, equals negative 6x plus 12. Step 3 is now to, of course, solve this new one variable equation. If you distribute it on the left, you get 3 minus 6x equals negative 6x plus 12. If we add 6x to both sides to get the variable on one side, you'll see we get 3 equals 12. It happened again. The x variable completely fell out. We only have a numeric statement now, 3 equals 12. And again, whenever you get a numeric statement where the variable's fallen out and you've done everything correctly, this puts you in one of the two special cases. Either there's no solution to the system or there's infinitely many. I want to examine this system again, and then we're going to come up with a rule of thumb that describes how to see from just the work up to here to see if you've got no solution or infinitely many solutions. We want to analyze this. We want to write each of the equations in slope-intercept form. We've already done that for the top equation. It's y equals 1 minus 2x. Let's do that now again for the bottom equation. So for the bottom equation, we simply need to divide both sides by 3. That would give us y equals negative 6x divided by 3 is negative 2x, and 12 divided by 3 is plus 4. So notice, and let me bring this down here for comparison purposes, I can also write y equals 1 minus 2x as negative 2x plus 1. Notice, these two lines have the same slope, but they do not have the same b value. They do not have the same y-intercept. So that means these lines are parallel, but they're not the same line. So that means they will never cross. Well, does that mean they have no solution? The system has no solution or infinitely many? Well, if the lines will never cross, then there's no solution. So this system has no solution. Let's summarize how to tell without having to do this additional work of writing the lines in y equals mx plus b form. If you go through steps 1, 2, and in step 3, you see that your variable has fallen out, and you get a numeric statement. For the last problem, we got 3 equals 3, and we ended up with infinitely many solutions. And in this case, we got 3 equals 12, and there's no solution. So let's describe essentially what's going on. This is a true statement. This is a false statement. 3 is not equal to 12. So anytime if you end up with a true numeric statement, then you've got infinitely many solutions. So true numeric statement, you've got infinitely many solutions. If you come up with a false numeric statement, that means there's no solution.